Welcome to Logic, Language and Information 1, brought to you from the University of Melbourne. I'm Craig Restall.
And I'm Jen Daverin. We're both passionate about logic and its applications. We have backgrounds in philosophy, mathematics, computer science and electronic engineering. We've been teaching logic at Melbourne for the last 10 years to students from the humanities, sciences and engineering. And now we're excited to bring this to a new audience from all over the world.
Now, logic is the study of information, wherever we find it, the features it has, how it's represented, and how we can manipulate it. Learning logic helps you formulate and answer all sorts of questions about information.
Logic plays a foundational role in several different disciplines, including linguistics, philosophy, electronic engineering, computer science, and mathematics. Logic provides a bridge linking these disparate disciplines, and as well as giving an access route into these individual disciplines by providing a common language and approach.
Now, over 5 weeks, we'll introduce you to propositional logic and some of its applications. We begin by introducing a formal symbolic language as a means to identify logical structure. Many of the sentences we speak and write contain logical structure words like if-then, and, unless, or, not, and things like this, which play an important role in combining information. Our formal language will help us precisely represent and understand and manipulate logical structure. You'll learn how the truth or falsity of a complex proposition like this one depends on the meaning of the logical connectives together with the truth or falsity of its simplest parts.
In developing the semantics or meaning of the logical connectives, we use structures called truth tables to make precise the way in which the truth or falsity of a compound proposition depends on its parts, the logical connectives and the simplest propositions. By convention, we use the symbol 1 for true and 0 for false. You'll learn how to use truth tables to make logical classifications and assessments, such as when one proposition is a logical consequence of another, or when two propositions are logically equivalent. In this example, the two highlighted columns of zeros and ones match exactly, and this shows that the two formulas are logically equivalent.
Now, truth tables are fine when it comes to small, not too complicated formulas, but they quickly become unworkable when things get larger or more complex. You'll learn an alternative means of making these logical classifications called proof trees, which are diagrams like the one that you can see next to us here. Crucially, you'll also learn why the method of proof trees always and only gives the correct answer, the so-called soundness and completeness of the proof tree method.
We cover core propositional logic in the first 2 weeks, and then in the remaining weeks 3 to 5, we offer 4 applications of propositional logic: electronic engineering, philosophy, linguistics, and in computer science. You are encouraged to choose 2 or more of the 4 application areas. All of the material for these applications will be released at the beginning of week 3, so that you can choose which order you take them in, and you'll have flexibility in completing the graded assessment for each of them. Digital systems is a core area within electronic engineering, and it is grounded in logic. The term digital systems covers the computer hardware inside all the communications and computing technology that we use every day, and which has changed our lives so dramatically over the last few decades. In this section of the course, we will introduce the simplest class called combinational digital systems. The most basic components are called and, or, and not gates, and these behave exactly as the logical connectives you will have learnt of in the core part of the course. You'll be introduced to several different ways of representing combinational systems, including circuit diagrams and logic formulas like the ones here.
The philosophy application section tackles the topic of vagueness, where a meaning isn't determined precisely enough for us to be able to decide every case. This is different from ambiguity, where a word has several different meanings. Now, you'll remember when we saw truth tables just before, they divided the world into cases where things are true and things are false. But if you look at this strip shading from red to yellow that's next to us, it's very hard to spot what place in the strip it makes a transition from saying it's true that this is red to no, it's false that it's red. The topic of vagueness makes people think that, well, maybe we've got to expand our understanding of truth values to have things beyond the truth values of true or false. At the very least, looking at vagueness helps us look critically at how the technology of truth tables and proof trees, how that applies to the world around us, which is sometimes hard to categorize. Now, in the next section, the linguistics section, we're going to be addressing the topic of implicature and implication. These are different ways of distinguishing what's implied in what people have said. So, for example, if somebody asks me, do I have any children, and I say in answer to them, I have a son, you'll often make the inference from this that I don't have any other children. But maybe I do. Literally, all that I said here in giving the answer is that I said I have a son, and that would be true if I have 2 children, 3 children, or more. But for some reason, for some good reason, when we say things like, I have a son, in answer to questions like this, you make inferences from what we say which goes beyond the logical content of what it is that we've said. In this topic, we're going to use the techniques that we've had in logic to begin to analyse this and understand how dialogue works and how we go beyond what we say to infer other things on the basis of what we've said.
And in the computer science applications section of the course, we're going to consider the task of automated reasoning, which is required of any artificial intelligence system. This is when and how we can program a computer to correctly calculate when a proposition is a logical consequence of a database of knowledge. You'll be introduced to logic programming using a language called PROLOG, and you'll learn how PROLOG works and when it can fail. PROLOG is used in the automated reasoning component of IBM's top-of-the-line artificial intelligence system called Watson. Watson's most public achievement was to recently beat all of its human competitors on a US TV game show called Jeopardy! So, how will we do all this? Well, there are video lessons, many of them with quizzes. Then there's the course notes for each section, which build up to make a textbook. Discussion boards are places where you can engage with other students. There are quizzes for each section. First, an ungraded practice quiz that you can take multiple versions of before sitting the graded quiz. And then some peer assessment tasks, which are short 500-word or so writing tasks.
Now, the grading of the course breaks down as 40% for the core areas of propositional logic, 40% for the different application areas, and then 20% for the final writing exam. The application score comes from taking your best 2 application marks out of 20, plus half of any additional application marks that you achieve, so that you'll get a reward for taking on 1 or more extra application topics. The final exam is peer assessed using a well-structured grading rubric that you'll see online. A score of 50 out of 100 is required for a statement of accomplishment in this course, and a score of 70 out of 100 is great, and you'll get a distinction. We have really enjoyed preparing this course, and we're looking forward to joining you, and we hope that you enjoy studying it with us.